Can I go up a little bit?
So like tau is defined. Can you go over the example of tau?
Tau is defined like this. Tau is the difference between the numerical approximation to the differential operator and the analytical differential operator operated on the same function.
And what was the problem of the equation at the start? What was the problem here?
The problem here is that I have the numerical differential operator operated on the numerical solution, while I have the analytical differential operator operated on the analytical solution. And they are not the same. As we can see, for example, in this case, they are obviously not the same. They are orders of magnitude different. Even for this case, they are not the same, and for this case, it's not the same, right? It's never the same. Okay. So if you remember our Taylor series analysis, it's only valid. Okay, so the way we derive tau, either order delta x or order delta x squared, is never valid if the two things are operated on different functions. Okay.
Is like tau analytical the same as tau numerical? Because in your second to last line, they're all analytical, right?
Right. Okay. So tau actually has to be defined on a certain function, right? So let's say tau. Yeah, this is tau analytical. Yes, that's right. If you plug in different functions, right, you get different taus. So here, what's driving the error equation is the truncation error, assuming you plug in the analytical solution. All right. Any other questions? Yes.
We don't know how to compute E, right?
Huh?
We don't know how to compute EI.
Well, do we know how to compute the EI? What's the initial condition for EI? 0, right? We started with the exact initial condition. Okay, and then the goal of this is to analyze how does the truncation error goes into EI and amplify. So we know at the very initial instant, the dEI dt is actually just tau a at t equal to 0. But as time evolves, the accumulation is not just without any dynamics. So this part is actually the dynamics of EI itself. Even without additional error coming in, the EI is going to either amplify or decay or stay just the same. And that's what distinguishes between these three cases. In this case, the error amplifies. In this case, well, although the truncation error is very large, but it doesn't amplify, it actually decays. While in this case, the truncation error is actually small because it's second order, but the error does not neither grow nor decay. So let's see how the dynamics is like for all the three cases. Okay, so what we want to focus on is the error equation without a let's just first look at it without any addition of truncation error. So if I just look at this equation without adding truncation error yet, yes?
How can you have an analytical truncation error? Because if it's analytical, shouldn't it be different? How can you have
The truncation error, the analytical truncation error is the difference between the numerical solution, the numerical differential operator and the analytical differential operator operated on the analytical solution. Okay. So the solution, the W is the analytical solution, but I'm applying two different operators on it. The difference won't be 0. All right. So that's the thing we are always being analyzing using Taylor series is we are analyzing the difference between numerical and analytical operators operating on the same function. And in this case, we operate on the analytical solution. Okay. So if we look at this equation and let's do the same Fourier analysis to figure out if the error is going to grow or decay or stay put. So if EI is going to be equal to, okay, we are going to say A as a function of t, ak times e to the j k 2 pi times I delta x. Okay, so that's our one term in a Fourier expansion. All right, where j is equal to square root of -1, k is the wave number that determines the frequency of this particular sinusoidal function. 2 pi just 2 pi, and I is the grid point. I delta x is the spatial location, right? So that's basically one term in a Fourier series. So then dEI dt is equal to, well, only the a term actually depends on t. So I'm going to take derivative to a, and the rest are the same. Okay, while the right hand side is e of I plus 1 minus ei divided by delta x is equal to the ak now is the same. So let's put 1 over delta x is also the same, and the rest is e to the jk 2 pi I plus 1 delta x minus e to the jk 2 pi I delta x. So is there any common terms in these two exponentials? Yes, if we can express the exponential of the sum into the product of respective exponentials, right? E to the a plus b is equal to e to the a times e to the b. So this plus can be split. Okay, once you split it, what you get is the common term is actually e to the jk 2 pi I delta x, and then we have 1 over delta x of e to the jk 2 pi, just the delta x, right? The I plus 1 is the 1 part, minus 1. Make sense? Okay. Now, what is that? Okay, so let's first match terms first. Because dEI dt has to equal to minus u times this thing, right? That means dak dt has to be minus u times akt times that thing. And the proportionality constant, I mean, this is again a linear differential equation, right? That it's of the type dA dt equal to lambda a, right? Except for the lambda here is now minus u times this now complex number. It's the first time we actually now get a complex differential equation. dA dt equal to lambda a, where lambda is complex. What's the behavior of that equation? I mean, in previous analysis, we looked at the same equation, same ordinary differential equation where lambda is real, right? We have either exponential decay or exponential growth. What if lambda here is complex? Yeah, growing oscillation or decaying oscillation, exactly. The frequency is controlled by the imaginary component, and the decay or growth is controlled by the real component. And now it's important to draw on the complex plane where lambda is. So the complex plane is a plane that is the x-axis is the real of lambda, and the y-axis being the imaginary part of lambda. So the location in the x-axis determines if the dynamics is growing or decaying, which in turn determines if the error is going to grow or decay, while the imaginary part controls how fast this oscillates. Okay, and if you remember in the first, I think in the second lecture, we did Fourier analysis for the analytical solution of the advection equation, right? And it turns out we get pure oscillation. Which means if you write the equation in terms of this equation, the lambdas are pure imaginary. It's going to be different. Now we approximate it with upwinding scheme, or with a forward difference scheme.